This video is about some special families of fractional linear transformations. Very briefly, we're going to get into characterizing which fractional linear transformations map the complex plane to itself, or map RP1 to itself, or map the upper half plane to itself, or the disk to itself. Okay, the easiest case to look at is fractional linear transformations that send the complex plane to itself. Now recall that we view the complex plane as sitting inside of CP1 by the following map. Z goes to Z1. And if we have a fractional linear transformation that sends the complex plane to itself, then something has to map to infinity, and the only point left is infinity itself, because fractional linear transformations are bijective. So for fractional linear transformations that send C to C, they have to send infinity to infinity, and that's all we really need to know. So we take a fractional linear transformation written in terms of a matrix A, and we see that it sends 1, 0 to 1, 0. This is our point infinity inside of CP1. And this just means that C in the matrix A has to be 0. And from this we get pretty quickly that the corresponding function from C to C is going to be just an affine function. So if we write out little f, it'll be az plus b if we normalize so that little d is 1, which we can do. So out of these easy observations, we get that if a fractional linear transformation maps the complex plane to itself, then it has to be an affine map, which just means it's of the form az plus b, where a is non-zero and b is just a complex number. Next, let's describe the fractional linear transformations that send RP1 onto itself. So recall RP1 was points in CP1 of the form ST, where S and T are real and not both 0. And so the theorem is stronger than we really need, but it'll be useful in a moment. The theorem will basically say that FLTs that map RP1 to itself can be represented using a matrix A with all real entries. So I put GL2R here, so you can use GL2R instead of GL2C, which makes sense. So the theorem states if I have a fractional linear transformation, and if it maps 3 distinct points in RP1 to points in RP1, then F has to map RP1 onto RP1, so you just have to check it on 3 points, and F can be represented using a matrix with real entries. Okay, let's try to prove it. Here's my proof over here. Okay, first note that if we just start with a point in CP1 and it actually is in RP1, how do you know that? Well, it just means that there exists a lambda you can multiply the entries by that will put you into the real numbers. And this is useful to point out because then I know that ZW equals lambda Z lambda W inside of CP1, and if these are real, they equal their conjugates. And then I can pull the lambda bar out, and then these are the original ZW is equivalent to Z bar W bar. So this is just a preliminary observation. Now I'm going to take my fractional linear transformation, F, and I'll write it using a matrix A, B, C, D. And let's plug in a point in RP1 into F. So it'll be written in this form, AS plus BT and CS plus DT. And now if this happens to be in RP1, then it'll equal its conjugate if I take the conjugates of the entries. So what I'm saying here is if I have ST in RP1 and F maps it to something in RP1, then I get this relation here. And I'm assuming in the theorem statement that I have this for 3 distinct points in RP1. Now what you'll notice here is that on this side I have points in the range of the FLT where you use A conjugate instead of A. So that says that FA and FA bar agree at 3 distinct points, and by the interpolation theorem, if 2 FLTs agree at 3 points, they agree everywhere. So you get FA is identically equal to FA bar. And then we mentioned earlier that 2 different representations can only come about if A and A bar are equal in PSL2C, meaning A is just a multiple of A bar. And you can actually adjust A so that it's equal to its conjugate by putting in multiples. So what I mean by that is, if A is equal to a multiple of A bar, you can just check one of A's non-zero entries that this will imply that this lambda has modulus 1. For instance, if the entry A inside of the matrix big A is non-zero, then you'll get A equals lambda A bar, and this would imply lambda equals 1 in modulus if A is non-zero. You'd just do that for any non-zero entry. And next, the trick is to take a square root of lambda with some mu, which will also have modulus 1. And then I take this equation here, and I multiply both sides by mu bar. Notice that mu bar times mu will give me 1, since mu has modulus 1. And so you get A equivalent inside of PSL2C to this matrix, mu bar A, which is equal to mu A bar. So this matrix equals its conjugate, so it has real entries. So I've found a representative of A that has real entries. Now if we declare B to be this matrix mu bar A, then F is represented with a matrix with real entries, and then it's evident that you send RP1 to RP1 if everything in B is real. When I plug in real stuff, I'm only going to get out more real stuff. So this gives a complete description of the FLTs that send RP1 to RP1. They can be represented using a matrix in GL2R. Now let's look at a nice corollary of this theorem, which is something geometrically obvious, but falls out of this approach pretty nicely, so I thought I'd mention it. Any 3 distinct points, A, B, C, and CP1, have a unique line in CP1 passing through them, using our earlier definition for a line in CP1, namely as the image of RP1 under a fractional linear transformation. So how do you prove this from what we've done? Well, let's say we have A, B, C, 3 distinct points in the image of RP1 under 2 FLTs. Then we get that FB inverse composed with FA maps these 3 distinct points in RP1 to points in RP1. Well, why is that? FA inverse of little a, if we plug it into this map here, it goes to FB inverse of A, and since A is in the image of FB of RP1, its inverse image will be in RP1. So this FLT sends these three distinct points in RP1 to RP1, so it has to send all of RP1 to itself. And now you apply FB on both sides, and you get that the image of RP1 under both FB and FA are the same. So these two images have to be exactly the same. So this is a line in CP1, it contains these 3 points. This is a line in CP1 that contains these same 3 points, and so the lines have to be the same.